Welcome back to our series on special relativity. In this video, I want to take a deeper dive into some things that are also related to special relativity that are of interest. One is mass increase, one is time dilation, which we've already covered, length contraction, and as we'll see on the next slide, we're going to see simultaneity is also an issue. Before we get started into the deeper dive of this segment, we have to make sure that we're clear on what we mean by moving through space-time or just moving through space. Let's take a look at our diagram on the left, and we need to note that the red vector, the red arrow on that diagram, represents me moving through space-time. And that is always equal to 186,000 miles per second, the speed of light. And the same with you. We are all moving, and everything is moving through space-time at the speed of light at all times. We all have a vector that shows that, and it can rotate. Now, let's say that you and I are sitting together at a table, and we're not moving relative to each other. That would mean that my red vector would point and lay on top of your black vector on the time axis. We'd be both aging at the same rate. But if I get in a spaceship and take off, then all of a sudden, I develop a projection of that red vector on the space axis. Now, the space axis shows in this diagram that I'm moving at 95% the speed of light. That's through space. But I'm still moving at fully the speed of light through space-time. So the faster I go, the more that red arrow rotates towards the space axis. But we need to be very sure that we understand that the space and moving through space is not the same as moving just through space-time. Space-time, again, you're always moving at the speed of light through space-time, but you aren't always moving at the speed of light through space. So let's go on from there. So now I want to talk just a little bit of math here for people. I want to point out that for those familiar with trigonometry, and if you're not, you might find this interesting also, but if you take this vector here that we got, which is me moving in my spaceship, through space-time at the speed of light, but through space at 95% the speed of light, we calculate that because here I'm putting the angle in. And in this case, the angle is 18.19 degrees. So what we need to do to find out how fast we're moving through space is we take the cosine of 18.19 degrees, as shown here, and that will give us our speed as a fraction of the speed of light. So here we're going 0.95 to speed of light because of we calculated the cosine of the angle. Most calculators have this, and the next one is the sine, which is how this vector projects on the time axis. And in this case, it points, the sine of the angle is 0.31. So that means for your second at the table, 1 second passes for you, and only 0.31 seconds pass for me in my spaceship. So the cosine is the projection of that vector on your space axis, and the sine is the projection of that vector on your time axis. In relativity theory, in special relativity, there is a factor that looks like this. It's the square root of 1 minus v squared over c squared. And if we put 1 over that, we get, as you can see here, 1 over the square root of 1 minus v squared over c squared. That's how it actually looks in special relativity. It is called gamma. It is part of the Lorentz transformations, and that is equal to 1 over the sine of our angle. I'm getting into this just to go into a little bit of detail on what's happening for those who are interested. Let's take a minute to talk about the speed of light. As I've said before, in space-time, you're always moving at 186,000 miles per second. That's our red vector. In space-time, 186,000 miles per second is how fast you're always moving. However, when we look at the projection of that vector on the space axis only, then we have to realize that we can only move slower than light. We can never get that red vector to lay directly on the space axis. Only light can do that, and it's the only position it has. But for us, or anything with mass, the only speed we can go on the space axis is less than light. We can never get to the speed of light. As I continue in this video, I'm going to be talking about not being able to ever reach the speed of light because of gamma. And I want to clarify that I am talking about the speed of a person through space, or a massive object through space only, the space axis. Remember, in space-time, you're always moving at the speed of light, but the projection of that red vector of, in this case, me and my spaceship, my projection on your space axis always has to be less than the speed of light, and I'm going to explain that right now. Because of this gamma that we just talked about, this gamma which describes what happens to things as they move faster and faster, the gamma is shown here. This is a plot of gamma. As you go faster and faster, as you approach the speed of light, you can see gamma starts increasing to infinity. So that's where time dilation also comes from. If you're going fast enough, 1 second on your clock at the table is only a very, very small fraction of a second on my clock. Getting back to mass increase, this is what happens to the mass of my spaceship as you measure it. As I approach the speed of light, if I go faster and faster, the closer I get to the speed of light, the higher my mass becomes. Well, mass is energy. And so in order to make the spaceship go faster, I have to keep inputting more and more energy. And pretty soon what happens as you approach the speed of light is all the energy you put into the spaceship becomes mass, not speed. And this line continues up to infinity, and so you can never get to the speed of light, nor can you exceed the speed of light on your space axis. Because the mass increases to infinity, you would have to input an infinite amount of energy, which you can't do. One other interesting thing about the speed of light is to realize that no matter what you're looking at, you're always looking back in time. This is the space-time equivalence also. If you look at your TV set or friend across the room, you may see them only a few micro, nano, or even attoseconds in the past, but you're still looking back into the past. If a star is 4 light years away, you're seeing that star as it was 4 years ago. The sun, it takes light 8 minutes to get from the sun to us. That means that the light from the sun is 8 minutes old when it gets here. If you look at a galaxy that's 2,500,000 light years away, you're seeing that galaxy as it was 2,500,000 years ago. So when you're looking at something, because of the finite speed of light, you are always looking into the past. You can never see anything as it is now. You are always looking into the past. Let's go into some other interesting things here. Let's look at length contraction. Backing up just a second, here was the point we were just discussing. Finite speed of light means everything you see is in the past. That's interesting. Okay, so moving on to length contraction. This is another effect that occurs when moving at high speeds, close to the speed of light. Let's say we're sitting at the table, again, you and I, and here's my spaceship. My spaceship is 5 units long, and we both agree at that on that measurement at the table. But then I get in my spaceship and I take off and I go, in this case, we're going 91% the speed of light. At 91% the speed of light, here's our cosine of a 25-degree angle, projects on your space axis as the speed of 91% or 0.91 the speed of light, sorry. All right, so, but what happens to the length of the spaceship? Well, to me, the spaceship is 5 units long like it always has been. However, if you look at the projection of the front and back of my spaceship on your space axis, we agreed that it was 5 units long at the table, but look what happened. Now that it's moving at 90% the speed of light, the back of the ship projects here, the front of the ship projects here, and so at the table it was 5 units long. Now you're looking at it projecting on your space and you're saying, nope, it's not 5 units. You only see that it's 2.1 units long. So the spaceship shrinks the faster it goes. So the faster the ship goes through space, the slower time goes on the ship, the shorter the ship becomes when you measure it, and the mass of the ship is increasing dramatically as you approach the speed of light. 3 things to keep in mind that I want to emphasize. Here's another one for you that's interesting, is when we talk about simultaneity, that two things both happen at the same time. Let's take a look at this spaceship up here. And if a flash bulb goes off here and a flash bulb goes off there, that's the back and the front of the ship. We'll both agree that the bulbs went off at the same time. We set them off at the same time, and we're sitting in the middle and we see them both go off at the same time. However, now if I get in my spaceship and take off at 91% the speed of light, and at that speed, now I'm going to set those two bulbs off at the same time in the ship. So I push the button, they both flash, and I say they both went off at the same time. However, look what happens with you. One end of the ship projects on your time axis here, and the other end projects here, because my ship is rotated in space-time. The ship has rotated in space-time. So now, when I say the events of the bulbs going off are simultaneous, you say, no, they're not. You see one bulb go off before the other one does. Very interesting effect. And I'm not going to go into a lot more detail. I just wanted to show some other consequences of special relativity. So we've got a few now under our belt. I'm going to show you real quickly here. This is what special relativity really looks like. This is called the space-time metric. You know something about this now. Whether you know it or not, you do know something about this. But this is the hyperbolic form of the equation, which is actually used and taught if you're in an academic circle or you're taking an actual relativity class. This is what you're going to see. You probably won't see the circle that I drew. You'll see this hyperbolic form. You don't have to worry about that. I just wanted to show it to you so you could see what the math actually looks like. So we covered a lot of ground. I think conceptually everybody gets this. And at this point, I just want to say that now that we've gone over all this, the special relativity, you've got a good piece of this under your belt. Hopefully you'll pursue it. There's a lot of great videos on the internet that talk about it in detail and in an academic form rather than a conceptual. But anyway, up to this point, you probably understand it. Here's general relativity. I may get into that at some point if I can figure out a simpler way to explain it, but this is where you get into actual curved space-time, gravity, black holes. The mass in the space tells the space how to curve, and the curvature of the space tells the matter how to move in that space. So some really interesting stuff. We've only hardly even scratched the surface. It's hard to even get started, but there's so much to all this, but it's all fun, it's all mysterious, and it makes a great mystery to solve. So thanks everybody for watching. I hope you learned something, and I hope it was fun, and I hope you keep going. Bye for now.